Again, welcome to second part of Unit 1 lectures. Again, this is Unit 1, Part 2 lectures. In Part 1, Unit 1, we talks about Boolean algebra, the Boolean identities, that is the rules for solving Boolean algebra problems. Here we're going to talk about logic gates and also how to design a logic circuit. We know that Boolean algebra goes with, again, logic gates. So here we're going to learn how to design simple logic circuits. Also understand how digital circuits work together to form a complex computer systems. I would say our computer CPU, the central process unit, consists of, again, billions of logic circuits, which perform different functions. So we have already looked at Boolean function in abstract terms in our Unit 1, Part 1 lectures. So in this session, we're going to see how Boolean functions are implemented in digital computer circuits, which we call the gates or logic gates. So we can see that the logic gates normally is an implementation of Boolean function or Boolean concept. So here we say a gate is an electronic device that produces a result based on two or more input values. And so our CPU, as I said earlier, most of the digital circuits or components consist of, again, logic circuits or logic gates. So in reality, gates consist of 1 to 6 transistors, but a digital designer think of them as a single unit. So we may see one gate or a logic gate. It should consist somewhere between 1 to 6 transistors. But as a designer or digital circuit designer, we think of it as a one unit. It's a logic gate, one simple gate is a one single unit. So IC, which is integrated circuit, contain collection of gates suited to a particular purpose. So as I said earlier, CPU, there are so many different purposes of CPU, computational. So a CPU is an IC, integrated circuit, which again will consist of so many different gates, each perform, again, different functions or purposes. So let's start with the most simplest gates. As we all remember, in Boolean algebra, we said the AND operator is the product, the OR operator is the addition, and then we have the NOT operator, which is the opposite negate. Not true is false, not false is true. Now you can see that we are using the same concept in logic gates. So we also have a logic gate called AND. And we can see that the truth table uses the same rule as a Boolean algebra. So for example, again, as we said earlier in Boolean algebra, the input can be more than 2. It shouldn't be 1 because 1 means we get the same output, 1. So 2 or more. Here we are using 2. So the truth table for AND gate is the same as the AND Boolean operator. If the 2 inputs are 0, the output is 0. If one of them are 0, the output is still 0. We only get 1 if all the inputs are 1. The OR gate is the same as OR Boolean operator. If all the inputs are 0, the output will be 0. If one of the inputs or all the inputs are 1, the outputs will be 1. So it's a sum and it's a product. Then the NOT logic gate truth table is the same as a NOT Boolean operator also. If it's 0, it's 1. If it's 1, it's 0. We also have extra, again, in the Boolean algebra, we talk about only 3 Boolean operators, the AND, OR, and NOT. But in logic gates, we have so many. For example, we have a gate called XOR. Another useful gate. XOR means exclusive OR. How this works is that if the inputs are the same, the output will be 0. If one of the inputs is different, then the output will be 1. Here we are using a gate 2 input again. So we can see if X and Y, they are all 0, the output will be 0. if X and Y, they are all 1, the output will still be 0. Unless one of them is 1 and 0. So for example, if I have 20 inputs, 20, and 19 of them is 0, and 1 is 1, my output will be 1. But if all the 20 gates are 0, and all the 20 gates are 1, the output will be zeros. So in short, exclusive OR or XOR means if all the inputs are the same, the output is 0. If the inputs are not the same, the output is 1. And this is the symbol for it. So it's kind of like an OR gate. We use the operator circle with a plus. So that's a special symbol again for XOR operation. We also have the NAND gate. NAND basically means not AND. So when we look at the truth table or even the symbol, we will see that NAND, N-A-N-D, is more or less like combining the NOT gate and AND gate together as NAND. So we say X, NAND, Y. Let's look at the truth table. Remember, if all the inputs are 0, AND gate means what? The output will be 0, but here is what? 1. When one of the inputs are 0, AND means it should be what? 0. But not AND. If it's 0, then it should be 1. When all the inputs again are 1, remember AND means we get 1. Not 1 means 0. So just looking at the truth table for NAND, the output gives us not AND. 0, 0, if it's AND, is 0. Not 0 is 1. 0, 1, 0 and 1 is 0. Not 0 is 1. 1 and 0 is 0. Not 0 is 1. 1 and 1 is 1. Not 1 is 0. So even looking at the symbol, you can say that we have the AND gate, logic gate circuit, but we have a small open circle, which means not. So you can see that X and Y will give me the product of X and Y, but what? Not invert or complement. We know N means X times Y. NAND means X times Y complement. So it's like not an N. The same thing applies to OR. In OR also, we said that if it's 0, 0, the output should be 0, but this time it's 1. So not OR, 1. Now we say in OR, 0 or 1 is 1, but not 1 is 0. 1 or 0 is still 1, but not 1 is 0. 1 or 1 is supposed to be 1, but not 1 is 0. So this is like all combined with not, and it's called NOR. So when you look at the first symbol, also the same thing. We have a OR gate symbol. The small circle, open circle, means not. So X and Y will give me X plus Y, but invert, not X plus Y. Now, using De Morgan theory, if I find the complement of X plus Y or invert, I will separate the invert as S invert times Y invert, and that's what we have here. S invert times Y invert is the same as S plus Y or invert, using De Morgan's theorem from Boolean algebra, our first part 1 lectures, unit 1, part 1. The same thing apply here. If I have X, Y, or invert, using the Morgan theorem, I will get X invert plus Y invert, and that's what we have here. So if I have X invert plus Y invert, then the symbol may change. It's like I have an OR gate because OR is plus. But the input, I have to invert it, so I put the open circles, which means to invert. So X inverted, Y inverted, they go through OR gate, you get S invert plus Y invert. So sometimes you may say this symbol as none, and this symbol also as none. And that's right, they are all the same. Same thing apply here. We can use OR with the not symbol outside, or we can invert both into AND because of De Morgan's theorem. So those are the NOR and also NAND. So far we cover 5 different logic gates: the AND, the OR, the XOR, the NAND, and the NOR. Now, we can use NAND and NOR, which are most common. And they're also known as universal gate because they are inexpensive to manufacture. And any Boolean function can be constructed using only NAND or NOR. So this NAND and NOR is a very common gate. So we have example here. I'm using a NAND. I have two input X, Y. And when I get these two X, Y into a NAND gate, I'll get invert of X and Y. But invert of X and Y together, going to another NAND gate, it will give us invert and inverse again. And remember we said that invert and invert cancel each other. So that will give me XY. So this means we are using two NAND gates to represent AND gate. As we can see, based on the output. Here we get the invert of XY. Now invert of XY goes as inputs here. We get XY invert and invert again because this is again NAND. And the complement of it will give us SY because we have complement, so both will cancel each other. In the NOT also, we can use and we have X. Since it's only one input, when it goes through here, we get X invert. In all, we are using 3 NAND. So we get, here we get S invert, here we get Y invert, and when they go through here, we get S invert, Y invert, multiply, all inverted. So using the Morgan theory, we can see that we get X invert invert plus Y invert invert. But invert invert will cancel, so we get X and Y plus. So this again, another concept of using NAND and NOR to produce a very simple OR, NOT, and OR gate. So gates also have a multiple input and more than one output. So example here, we can have a gate with two input X, Y, but our output also will be Q and Q invert. It's possible. Maybe the second output here can be provided for the complement of the operation. And we may see this example more later on. So example here, we can have 3 inputs, which will give a combination of 1 input. So since this is going to OR gate, it will be S plus Y plus Z. And the same thing, this is going to AND gate, so it will be S times Y invert times Z invert. So the main thing to remember is that a combination of gates implement a Boolean function. And as we said earlier, almost all the IC circuits consist of more gates, 2 or more logic gates. So for this, a very good example they gave us here. Here we have a combinational circuit which consists of 3 different types of gates. 1 NOT gate, 1 AND gate, and 1 OR gate. And the inputs are 3. At the end, we get an output of X plus Y invert Z. If we remember, we use this expression to, again, develop the truth table, to create the truth table. I can also use this expression from the truth table. I can create a combination circuit. So if a combination circuit is given to me, I can develop or create a truth table. If a truth table given to me based on the output of each scenario output, I can create a combinational circuit. So here, for example, I look at the expression, they say, oh, X. Okay, X is an input and it goes to plus, it goes to Y. But Y is not plus there. We have Y invert plus Z. So I need a NOT gate to change Y to Y invert. That's what we did here. And multiplication comes first before addition. So since I have Y invert times Z, I'll put N, multiplication will give me N gate. So this output here will be Y invert Z because I have Y invert, Y go through NOT, it gives me Y invert. And Z with Y invert go through N gate, and I'll get Y invert Z. Now Y invert Z will be an input to OR gate because we have a plus. and X is by itself, so S also comes. So the output will give me S plus Y invert C. So this is one of the reasons why in chapter, the unit 1, we were talking about Boolean algebra. We always have to simplify the expression to make it very simple. Now, the less operators we have here, the less gates we have in a circuit, which will be more economically and more efficient. So this is an example of a digital component. Here we say a standard digital components are combined into a single IC package. So this can be any digital circuit, even can be an CPU or a memory or something. So we say Boolean logic can be used to implement the desired functions. So based on the logic gates we have, this very circuit will perform a specific function. But our point here is that every digital component consists of logic gates in different form based on the function that is going to perform. A memory, most of the time the CPU, so many different functions, so many combination of logic gates. And this is a Boolean circuit. Example, we have two input, X and Y. This Boolean circuit consists of only two logic gates, NOT and AND. NOT will invert my X, so I'll get S invert. Now I have S invert going to N, and also I have Y going to AND gate. So the output should give me X invert Y. This also can be rendered using only NAND gates, but look, the two circuits will give me the same solution, the same output as we can see here. But here you can see that we are using more circuits. How this works, let's go through step by step. We get X first, we put X into NAND, so we get X invert. Then we have X invert as one input with Y. And when we put it into a NAND gate, we get X invert times Y or invert. Using the Morgan theory, I'll get S invert invert, so it will be X. Product will be addition. Y will be Y invert, so I get S plus Y invert here. So now S plus Y invert is going through another NAND gate, which means we are going to invert everything. So we get S plus Y invert or invert. And using our expression, the Morgan theory again, this will give me X invert, plus invert will be multiplication. Y is already invert, so it will give me Y invert and invert. So the two invert will cancel. And I'll get X invert times Y. So we can see these two circuits are doing the same thing. They are performing the same function based on the output. Also, we can wire the pre-packaged circuit to implement our function. So we can put it as a one package system. And the Boolean logic also is used to solve practical problems. Expressed in terms of Boolean logic, practical problems can be expressed by truth tables. And this is one of our assignments in Unit 1 assignment. An expression is given to us. We have to come up with a truth table, and from the truth table, we have to develop the circuit, the logic circuit. So truth tables can be readily rendered into a Boolean logic circuit. We have an assignment like this, and we saw an example also. So suppose we are to design a logic circuit to determine the best time to plant a garden. We consider three factors here. Best time to plant a garden. One will be the time, where 0 represents day and 1 represents evening. 2, the moon phase, where 0 represents not full moon or 1 represents full moon. And of course, the temperature, where 0 represents 45 degrees. Here we can see that we are dealing with a digital circuit. So it's more or less a logic circuit, 0 or 1. So we are representing 0 and 1 to mean something. Planting a garden, of course, the temperature, the atmosphere we consider maybe the sun, the moon, the temperature, the health, what attributes or what characteristics affect the health atmosphere. So the time, evening or daytime, the moon, is it full or not full? Also the temperature, is it over 45 degrees or less than 45 degrees Fahrenheit? So if we know these three conditions, we determine that the best time to plant a garden is during the evening with a full moon, maybe after we design the circuit to implement. So this results in the following truth table. Remember, we have time can be 0. When we say 0, it means what is represent day. 1 means evening. Moon, half, not full, 0. If it's full, 1. Temperature, 45, 0. And below represent 1. So we come up with these combinations. And also the temperature is given to us. We remember we say if it's 45 is 1. And sorry, 45, 0, below 45 is 1. So this time, moon, and temperature, based on the condition, we came up with all the possible combination. And I'm designing a circuit for this. So based on this combination now, we can get whether we should plant or not. So we only going to plant will be based on 1. We determine that the best time to plant a garden is during the evening with a full moon. Again, based on this condition given to us. We draw the truth table based on this condition. So we can see, we see 0, 0, 0 here. 0 here means the temperature is, I think, above 1. Let's go back. 0 means represent 45 degrees and 1 represent over 45. So the temperature, and we know the time, the daytime and the evening time. Moon is not full, and its full is 1, etc. So we have this combination based on the condition. Then we come up with this truth table. But we have a condition here. So this means we're going to design the circuit. So we came up with a circuit based on the truth table. So combinational circuit, again, we have designed a circuit that implement the Boolean algebra. We saw this in the previous. This circuit is an example of a combinational logic circuit. Why? Because it consists of more than one type of logic gate. So here we say a combinational logic circuit produces a specified output almost at the instant when the input values are applied. And in the later section, we're going to explore a circuit where this is not the case. For example, we have sequential circuits, which again depends on activities in sequential order. So a combinational logic circuit gives us many useful devices. And one of them is the example here, which we call the half adder, which finds the sum of 2 bits. We gain some insight as how to construct the half adder by looking at its truth table shown at the right there. So you can see here, I have input. I'm adding 2 numbers. So that's why input is X and Y. And now we know that 0, 0 will give me 0, 0, 1 will give me 1, 1, 0 will give me 1, 1, 1 will give me 0, remainder 1. Actually, in the Boolean algebra, 1 plus 1 is 0, remainder 1. 0 plus 0 is 0, remainder 0. 0 plus 1 is 1, remainder 0. 1 plus 0 is 1, remainder 0. But 1, 1 is 0, remainder 1. Then 1 plus 1 plus 1 is 1, remainder 1. So based on this truth table, I can look at, so okay, I can construct my logic circuit here, combinational logic circuit. Why? Look at the sum. We can see that when the inputs are the same, we get 0. When the inputs are different, we get 1. So this is a XOR gate. So I can come with a XOR gate with 2 X and Y going in. And when you look at here, it's an AND gate because we only get 1 when all the inputs are 1. So which means a half adder or a logic circuit that can find a sum of 2 numbers uses a logic circuit with two gates. One is XOR and one is AND. And that is the circuit here. So we have input XY. You can see that we are using the XOR to give us the sum. The carry will be the AND gate of SY. Got as the carry, and that's the sum. And this is how, again, we take our time to design circuits. Here they say we can change our half adder into a full adder. A full adder, we are using 3 inputs now. We get X and Y, then carry in, then the sum and carry out. So the truth table is, if the truth table is given, we can look at the truth table to come up with the design of the circuit. And here we can see that when everything is 0, 0, when the carry in is 1 and the input are 0, we get 1. And the list keep going. And this is the circuit. How can we change the half adder shown below to its full adder? We have to look at the circuits here. The truth table, sorry, and see the output. So we can see that when we have 0, 0, and 0, we get 0. 0, 0, and 1, we get 1. 0 and 1, 0, we get 1. Now 0, 1, 1, and 1, we get 0, carry 1. So all 0, 0, 0. When we get only 1, 1, remember 1. When we get only 1 again, the same thing. Now when we get 2 1s, remember we said that 1 plus 1 is 0, carry 1. Here we have only 1, so it's 1, remember 0. Here we have only 2 again, so 0, 1. Here we have 2, 0, 1. 1 plus 1 plus 1 is 1, remainder 1. So we are doing the same thing as we did for the half adder. Just add 0 plus 0 plus 0 is 0, remainder 0. 0 plus 0 plus 1 is 1, remainder 0. 0 plus 1 plus 0 is 1, remainder 0. 0 plus 1, 1. 1 plus 1 is 0, remainder 1. 1 plus 0, 0 is 1, remainder 0. 1, 1 again is 0, remainder 1. 1, 1 again 0. 1, 1, 1 will be 1, remainder 1. So now I can look at this circuit and see what kind of gate I can use. I have to consider having my 3 inputs with only the sum. And this is what we came up with. We have to be very careful here. The previous one was very straightforward. We saw the 2 outputs so easy. But here we have input of X and Y. So we can see that first, we take our input to get the sum. So when we have X, Y, we want it to go through the XOR. Why it should go through the XOR? Because we can see that 0, 0 is 0 here, but 0, 0 here is no more 0. So this is why we need 2 circuits, more than 2 gates now. So we have X, Y go through the XOR, then we get N, and then N will go through OR. Then output of this will give me another carry in inputs to the carry out, and then the sum. So this sum here, we can see that if we have 0, 0, the output here should be what? It should be 1. 0, 0. I mean, sorry. If the input are the same, we get 0. Now, if I have 0, 0 and I get 0 here, this 0 will go through another XOR gate. And if I have 0 here, and the carry in was also 0, then my sum will be 0. And that's what I have for the first. I have 0, 0. Then the 0 is coming. Carry in now is 0. So 0, 0, 0. Now, let's go to the second one. I have 0, 0 again. When I reach 0, 0, here will be 0, of course. By this time, the carry in is 1. So carry in is 1. We get 0, 1. If we get 0 and 1, remember what we said. If the XOR, if the inputs are different, the output will be 1. So we get 1. And we can keep going, 0 and 1. If I have 0 and 1 here, this will be what? The inputs are different, so this will be 1. If I have 1 here, And then the output also is 0, which is the third one. So since 0 and 1, the output also will be what? 1. I'll do one more again. I don't want to waste time here. Let's do the last one. S is 1, 1. So I have 1, 1 here. Oh, if I have 1, 1, then it should be 0 here. So if it's 0 here and the carry in is 1, then 0 and 1, the output should be 1. So we have 1. So this is how we have to, looking at the truth table, we can take our time again to come up with the circuit. So just as we combine half harders to make a full harder, full harders also can connect in series. And this can come with a concept we call the ripples. The carry bit ripples from one harder to the other next, etc. And actually we saw that, let me go back here. We can see that this is a ripple effect. We can have more circuit. You see, when I get my input here, I take another one, get input, I can take another one, get the input, or the carries, etc. And also we have something we call decoder. This is another example of a combinational circuit. Decoders are another important type of combinational circuit. Among other things, they are very useful in selecting memory location according to a binary value placed on the address line of the memory code. So address decoders with n input can select any of the 2 to the power n locations. So if I have n input, I can get 2 to the power n output. And another example is, this is what a 2 to 4 decoder looks like. We have 2 inputs, but the output will be 4. So different combinations. We also have what we call the multipressor. A multipressor it's not just the opposite of multipressor does just the opposite of a decoder. So you can see that here we have more input with less output. With a decoder, we have less input, more output. So just the opposite. And this is a 4 to 1 multipressor, which means we got 4 input, it gives us 1 output. And this is where I'm going to end the lectures. This is again our part 2 lectures in logic, circuits, and gates. And this covered discrete mathematics part of the course. Thank you. Bye.